What is matter? What do a smooth stone, a wisp of steam, and the quiet breath rising from your chest have in common? They are all made of matter. Matter is anything that takes up space and has mass. It is the stuff of everything, the fabric of the physical world. It can be soft or solid, weightless or heavy, visible or invisible. But if it exists, if it has presence in space, it is matter. Matter comes in different forms. Solids hold their shape, like a spoon or a tree trunk. Liquids flow, like rainwater down a window pane. Gases spread and drift, like the air that surrounds you, unnoticed but always there. Even light, in some ways, dances with matter. And deep in the quantum world, particles can blur the line between energy and mass. But at this level, we stay grounded in what we can almost feel, the quiet comfort of the physical. Now, if you zoom far, far in, past what your eyes can see, you'll find that even the most solid object is mostly empty space. Inside every atom is a tiny nucleus, surrounded by electrons in motion. Between them is vast nothingness, the kind of emptiness that feels infinite. And yet all those atoms, mostly space, come together to form stars, oceans, trees, and you. Matter isn't just what things are made of. It is the quiet assurance that there is something here, something to touch, something to rest on, something real. Mass and volume. Picture a beach ball and a small rock. The ball is large, light, easy to lift. The rock is small but dense, surprisingly heavy. This is the difference between volume and mass. Volume is how much space something takes up, how big it appears. Mass is how much matter is packed inside, how much substance it truly contains. You could fill a balloon with air until it grows huge, yet its mass remains light. Meanwhile, a piece of lead could sit quietly in your hand, heavy despite its size. Two objects might look the same, but feel entirely different. A sponge and a brick, a snowflake and an ice cube. Their volume could be equal, but their mass tells another story. Mass never changes, no matter where you are. On Earth, on the moon, drifting in space. But weight, the pull of gravity on that mass, can shift. Volume, on the other hand, can stretch or compress, depending on temperature, pressure, or force. Together, mass and volume whisper something simple, yet profound. Appearances are only part of the truth. There is always more within, more depth, more density, more to understand than what you first see. The concept of force: gently push a swing, feel it move forward, pull a drawer open, watch it respond to your hand. What made that happen? A force. A force is a push or a pull applied to an object. It can start motion, it can stop it, it can change its direction or its speed. Forces are invisible, but their effects are all around. A gust of wind, the tension in a stretched rubber band, the quiet pull of the earth on your feet. There are many types of forces. Contact forces, like friction or tension, need things to touch. Then there are forces that act at a distance. Gravity, magnetism, electric fields. They reach across space like unseen threads tugging at the world. Every force has a direction and a strength. You may not see it, but you feel it. In the way your body stays grounded, or how a ball arcs through the air when thrown. Forces don't just cause change, they are change. Every movement, every shift, every moment of action in the universe begins with a force. Even now, as your chest rises and falls with each breath, your muscles are applying tiny forces, steadily, gently, naturally. Gravity we feel every day. Why do things fall? Why do you stay on the ground, even as the Earth spins through space? The answer is gravity, the quietest, most familiar force of all. Gravity pulls every object with mass toward every other object with mass. It's what keeps your feet on the floor, your head on the pillow, and the moon circling the Earth. You might not feel it as a push or a tug, but it's always there, holding you close to the planet, like a soft, invisible embrace. It doesn't need contact. It doesn't flicker or fade. Gravity is constant. The more mass something has, the stronger its pull. That's why the Earth keeps everything drawn to its surface. and why the sun holds the planets in orbit from millions of miles away. You don't have to think about it. You just exist within it. It's part of your every movement, every step, every fall. And as you lie still, gravity cradles you. Steady, silent, patient. Motion and rest. A leaf drifts down from a branch. A river flows slowly. You blink, you breathe. This is motion. Motion is simply change in position over time. Something was here. Now it's there. And rest? Rest is the absence of motion. Stillness, calm, balance. But even stillness is relative. You may feel completely still, lying in your bed, yet the Earth spins at over 1,000 kilometers per hour and orbits the sun at nearly 30 times that speed. The sun itself moves through the galaxy. So really, you are in motion, always. We define motion by choosing a reference point, a tree, a floor, a sky. Without that, motion becomes abstract, elusive, endless. An object in motion will stay in motion unless something acts on it. An object at rest will stay at rest. This is a quiet law of nature, simple but deep, one of the great truths of how the world moves. Motion is life, rest is pause, and both exist together like night and day, like inhale and exhale. Speed versus velocity. A train glides across the landscape. A bird flies through the sky. You walk slowly to the window. All of these are motion, but how do we describe it? We begin with speed, how fast something moves. If you drive 60 miles in 1 hour, your speed is 60 miles per hour. Simple, directionless, just a number telling how quickly something covers distance. Velocity, though, is more than speed. It adds direction. Not just how fast, but where to. A car moving north at 50 miles per hour has a different velocity than one moving east at the same speed. Speed is a whisper, velocity tells a story. And because velocity includes direction, it can change even when speed stays the same. A runner on a circular track may keep a steady pace, but their velocity is always shifting, curving with the path. Velocity brings elegance to motion. It allows us to speak not just of movement, but of purposeful movement, the kind that flows, turns, or reverses. Speed tells you how much, but velocity tells you what way. In physics, that subtle difference shapes everything. Acceleration. What happens when you press harder on the gas pedal, or when a ball falls faster as it drops? That change, that growing or shrinking of velocity over time, is acceleration. It doesn't only mean getting faster. Acceleration can also mean slowing down or changing direction. Anytime velocity shifts in magnitude or direction, acceleration is there. If you're riding a bike and start to pedal harder, you accelerate. If you pull the brakes, you're still accelerating, just in the opposite direction. Even turning a corner counts as acceleration because your direction changes. Acceleration can be gentle, like the slow rise of a hot air balloon, or sudden, like the jolt of a roller coaster launching forward. On Earth, the most familiar acceleration comes from gravity. It pulls every falling object downward at about 9.8 meters per second squared, a precise, patient tug that speeds up everything, no matter how heavy or light. Acceleration is what gives motion shape. It curves the path, bends the timing, and breathes change into movement. Friction. Slide your hand gently across a table. Feel the resistance? That's friction. Friction is the force that opposes motion between two surfaces that touch. It's the reason things slow down, stop, or never start moving at all. Without friction, your feet would slip on the ground. Cars couldn't grip the road. You couldn't hold a pen or button a shirt. There are different kinds. Static friction keeps something still, like a box that won't budge when you push it. Kinetic friction slows it down once it moves. Air resistance is a kind of friction too, between moving objects and the air around them. Though friction resists motion, it also makes life possible. Walking, writing, climbing, all depend on it. It creates heat too. Rub your hands together. Warmth builds from the struggle between surfaces. In machines, friction can be wasteful, creating wear and loss. But in nature, it's essential. a quiet, constant presence that adds texture to movement. Friction is the invisible grip of the world. Air resistance. Drop a feather in a rock from the same height. Watch how differently they fall. What slows the feather, letting it drift and dance? That's air resistance, a special kind of friction between a moving object and the air it moves through. When you run, you feel the air push against you. When a car speeds down the highway, it slices through the atmosphere, and air resists. It presses back, gently or forcefully, depending on shape and speed. The faster you go, the more resistance you feel. A skydiver plummeting from a plane reaches something called terminal velocity, the point where air resistance balances gravity. Falling stops accelerating. It becomes steady, smooth, final. Designers of planes, cars, and rockets study air resistance closely. They shape their machines to reduce drag, to glide instead of struggle. Air resistance is invisible, but never absent. It's the breath of the atmosphere pushing back. Not to stop you, just to slow you, to ask if you're sure. Balanced and unbalanced forces. Why does a book lie still on a table? Why does it only move when you push it? The answer is balance, or lack of it. When forces acting on an object cancel each other out, we say they're balanced. No movement happens, no change. Everything stays still or continues moving smoothly, just as it was. But when forces become unbalanced, motion begins. A stronger push, a shifting pull, a sudden nudge. The object responds, accelerating in the direction of the greater force. It's like a tug-of-war. If both sides pull equally, the rope doesn't move. But the moment one side pulls just a little harder, the balance breaks and the motion begins. Balanced forces bring stillness or steady motion. Unbalanced forces bring change. And in physics, change is everything. Newton's first law. A ball lies motionless on the floor. It doesn't roll. It doesn't slide. It simply stays. Unless something acts on it. Newton's first law tells us an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This is the law of inertia, the quiet stubbornness of matter. Inertia is not resistance in the angry sense. It's more like loyalty. Objects remain loyal to their state, stillness or movement. A glass won't slide off a table on its own. A moving train won't stop without friction, brakes, or drag. Motion continues. Stillness remains. It's why when a car suddenly stops, your body lurches forward. Your body wants to keep moving. It's inertia, a soft but powerful instinct of physics. And it's everywhere. A planet stays in orbit. A spinning top continues turning. The air you exhale keeps drifting. Everything wants to continue being what it already is, until something asks it to change. Newton's second law. Push gently, the object moves slowly. Push harder, it moves faster. This is Newton's second law, the relationship between force, mass, and acceleration. The law is simple. Force equals mass times acceleration. F equals ma. If you apply the same force to a heavy object and a light one, the lighter will accelerate more. If you want the same acceleration in both, you need to push harder on the heavier one. It's a quiet truth about how the universe responds to effort. More mass, more resistance, more force, more change. This law isn't just about objects. It describes motion itself. How things begin, how they change direction, how they speed up or slow down. It's not emotional, not judgmental, just mathematical, predictable, constant. The engine behind every shifting wind, every falling star, every gentle nudge. F equals ma is the heartbeat of classical mechanics, a soft equation that speaks the language of movement. Newton's third law. Press your hand gently against a wall. Feel it pressing back? That's Newton's third law. For every action, there is an equal and opposite reaction. It sounds like poetry. And in a way, it is. If you push a chair, it pushes you back. If a rocket blasts downward, it lifts upward. Walk forward, and the ground pushes against your feet. Even the air responds when you move through it. Action and reaction. a perfect balance, a conversation between objects, a silent handshake of the universe. You don't always see both sides. When you jump, it's the Earth that pushes you up, but you also push down on the Earth, though it's so massive it hardly moves. This law reminds us, nothing acts alone. Every force is part of a pair. Every motion is a dialogue. Even in stillness, there are echoes. Even in action, there is balance. Linear momentum. Imagine a train moving quietly across the tracks. Heavy, steady, calm. That train has momentum. Momentum is the product of mass and velocity. How much motion something carries. The more mass, the more speed, the greater the momentum. It's why a small pebble tossed at you is harmless, but a fast-moving baseball stings, or why a massive truck takes longer to stop than a bicycle. Momentum isn't just about movement. It's about the persistence of movement. It's stored energy in motion, the body's memory of being in motion. And in physics, momentum is conserved. In a closed system, the total momentum remains the same, even if objects collide, bounce, or change direction. Like dancers shifting partners, but never losing the rhythm. Momentum flows from one object to another, quiet, mathematical, perfect. Impulse. Stand still, then suddenly someone taps your shoulder. You move. That tap was small, but it happened fast. Impulse is the product of force and the time it's applied. A quick, powerful push, a change in momentum. The formula, impulse equals force times time. A tiny force over a long time, or a large force over a short moment, both can cause the same change. It's the duration and the strength that matter. A soft catch slows the ball gently, spreading the force across time. A punch delivers force instantly, a sharp impulse. In physics, impulse is how motion changes. It's the push that shifts you from one state to another. The reason airbags exist, the reason jumping from high places hurts, or doesn't if you land in soft sand. Impulse is the bridge between force and momentum, the quiet moment where change begins. Work. When you push a heavy box across the floor, you're doing work. In physics, work isn't just effort or sweat. It has a precise meaning. Work is done when a force moves an object in the direction of that force. If you apply force, but nothing moves, there is no work, no matter how hard you push. The formula is simple. Work equals force times distance times cosine of theta, where theta is the angle between the force and direction. If the object doesn't move, or if you push straight up but it slides sideways, no work is done in the direction of motion. Lifting a book, that's work. Pushing a sled, work. Holding a heavy bag still, no work in physics terms, even though your arms may disagree. Work transfers energy. When you lift something, you're giving it potential energy. When you push it, you're giving it kinetic energy. You're feeding motion, or resistance to motion. It's a quiet transaction. Work is the bridge between force and energy, a whisper passed from one form to another, through effort, through distance, through motion. Energy, kinetic and potential. Energy is everywhere, but you never see it directly. You only see what it does. In physics, energy is the capacity to do work. It exists in many forms, but at its core, it flows between two fundamental types, kinetic and potential. Kinetic energy is energy of motion, a rolling ball, a flying bird, a gust of wind. The faster something moves and the more mass it has, the more kinetic energy it holds. It's movement itself, distilled into form. Potential energy, on the other hand, is stored, waiting, like a rock on the edge of a cliff, like a stretched rubber band. The energy is there, but quiet, hidden in position or tension, ready to be released. Raise an object and you give it gravitational potential energy. Stretch a spring and energy builds. The moment it moves, potential transforms into kinetic. Silent promise becomes active change. Energy can't be created or destroyed, only transformed. Kinetic into potential, potential into motion, light into heat, food into movement. It's a soft, endless cycle. You are made of energy. You carry it, release it, store it, share it. Even now in stillness, your body hums with silent energy. Conservation of energy. You light a match. It burns. The flame dances and warmth spreads. Where did that energy come from, and where does it go? Physics answers simply, energy is never lost, only transformed. This is the law of conservation of energy. Energy can shift from one form to another, from chemical to thermal, from mechanical to electrical, from potential to kinetic. But the total amount, the sum of it all, remains the same. Imagine a swinging pendulum. At the top of its arc, it holds potential energy. As it falls, that potential becomes kinetic. Then, as it rises again, kinetic becomes potential. Back and forth, never gaining, never losing, just changing form. Even when energy seems to vanish, like heat lost in friction, it's still there, just spread thinner, harder to gather, less useful, but not gone. This law tells us that the universe is a perfect ledger. Every movement, every reaction, every change balances out. Nothing is wasted, nothing disappears. Energy is eternal, it only shifts its shape. Power. Two people lift the same box. One does it slowly, the other lifts it quickly. They do the same amount of work, but one used more power. Power is how fast work is done, how quickly energy is transferred or transformed. The formula is simple. Power equals work divided by time. Lift something faster, and you've used more power. Burn fuel more quickly, and you release more power. It's not just about doing something, it's about how rapidly you do it. The unit of power is the watt. 1 watt means 1 joule of work per second. A light bulb, a microwave, a wind turbine, all express their usefulness through power. Power can be massive, like a rocket launch, or tiny, like the warmth from a candle. It doesn't always roar. Sometimes power is patient. It's the quiet engine beneath action. Not just what is done, but how swiftly it flows. Simple machines, a ramp, a lever, a pulley. These are not just tools, and they are ideas. Simple machines are devices that help us do work more easily. They don't reduce the total amount of work, but they spread it out, redirect it, transform it into something more manageable. A lever lets you lift something heavy by using a longer arm. A pulley changes the direction of a force. A wheel and axle reduces friction. An inclined plane lets you lift by pushing. A screw transforms rotation into linear force. A wedge concentrates force into a sharp edge. These machines take advantage of ratios, distance versus force, time versus effort, to give us control. They are ancient and elegant, the same tools used to build pyramids, to raise sails, to lift gates, to move stones. But the real beauty of simple machines is not in their parts. It's in how they show us the deep truth of physics, that work can be done in many ways, and that cleverness can turn effort into grace. Oscillations. A swing moves back and forth. A string vibrates after being plucked. A heart beats. These are all oscillations, repeated movements around a central point. An oscillation is a kind of rhythm. Something shifts one way, slows, returns, then shifts the other way, over and over, like a cradle, like the tides, like your breath. At the core of most oscillations is a restoring force, something that pulls the system back toward equilibrium. Stretch a spring, and it wants to return. Displace a pendulum, and gravity pulls it back. That return creates motion, and the motion overshoots, only to be pulled back again. The time it takes to complete one full swing, from start to return to start again, is called the period. Shorter periods mean faster oscillations. Longer ones bring slow, graceful motion. Oscillations are everywhere, in atoms, in sound, in stars that pulse, in the quiet ticking of a clock. They bring structure to time, to music, to motion itself, a steady dance between force and return, tension and release. Simple harmonic motion. Take a mass on a spring or a swinging pendulum. Move it gently. Let it go. It begins to oscillate in a pattern that's smooth, predictable, and beautifully mathematical. This is simple harmonic motion. It occurs when the restoring force is directly proportional to how far something is displaced from equilibrium. Pulled twice as far, the force pulling back is twice as strong, like the spring gently saying, "Come back." The motion traces out a sine wave, soft, curving, endless, back and forth with perfect regularity. This kind of motion is idealized. In real life, friction and resistance slow it down, but in theory it goes on forever, like a note that never fades or a planet that never stops orbiting. Simple harmonic motion is the foundation of so many systems. Sound waves, vibrating strings, the tuning fork, even quantum particles in certain states. It is repetition without chaos, precision without effort, a lullaby written into the physics of motion. Pendulums. A pendulum is one of the oldest and most soothing forms of motion. Picture a weight hanging from a string. You pull it gently to one side, then let go. It swings back and forth, back and forth. Its motion is regular, predictable. The period, the time it takes for one full swing, depends mostly on the length of the string and the gravity pulling down. The mass of the bob doesn't matter, only how long the arm is and how deep gravity tugs. Galileo noticed this in the 1600s, watching a swinging lamp in a cathedral. He timed its rhythm with his pulse. That rhythm became the heartbeat of early clocks. Pendulums resist change. Once moving, they continue, and the wider you pull them, the stronger the return. They're used to keep time, to measure gravity, to reveal Earth's rotation, but they also soothe the senses. Gentle, repeated motion, like breath made visible. Pendulums remind us that even in change, there can be peace. Wave properties. A wave is not a thing. It is a disturbance, a ripple that moves through space or material, carrying energy but not matter. Drop a pebble in water, you see circular waves spreading outward. Strike a drum. Waves pulse through the air. Wiggle a rope. Waves move down its length. All waves share certain properties. Amplitude. How tall the wave is, the strength, the energy. Wavelength. The distance from crest to crest, or from any point to its repeating twin. Frequency. How many waves pass a point each second? Speed. How fast the wave moves through the medium. The higher the frequency, the shorter the wavelength. The greater the amplitude, the more energy the wave carries. Waves can reflect, bounce, combine. They can build each other up or cancel each other out. Two waves in the same space don't collide. They overlap, flow through one another, then move on unchanged. Waves are in water, in sound, in light. They shape everything we hear, everything we see, even how atoms behave. They are patterns, not particles, movements, not things, music, not matter. Transverse versus longitudinal waves. Not all waves move the same way. Transverse waves move energy in a direction perpendicular to the motion of the particles. Imagine shaking a rope up and down. The wave travels forward, but the rope moves side to side. Light waves, water waves on the surface, vibrations in strings. All are transverse. They ripple across. Longitudinal waves, by contrast, move energy in the same direction as the vibration. Think of sound. Particles of air compress and expand along the line of travel, like pushing and pulling a slinky. You don't see the air move, but the energy travels from mouth to ear, from explosion to echo. These compression waves carry voices, music, thunder. Some materials carry both types. Earthquakes ripple with transverse shear waves and longitudinal pressure waves. Your body can feel both, through skin, through bone, through the spaces in between. Understanding how a wave moves tells us how it behaves, how it reflects, how it carries energy, how it fades or strengthens. Whether side to side or push and pull, a wave is always movement made visible, vibration made meaningful. The speed of sound. You clap your hands and a moment later the sound reaches the far wall. Sound travels. not instantly, but at a speed that depends on the world it moves through. In air, at room temperature, sound travels at about 343 meters per second, or roughly 1,235 kilometers per hour. Fast enough to circle a small city in seconds, but still slow compared to light. The speed of sound changes with the medium. In water, it's faster, about 1,500 meters per second. In steel, faster still, more than 5,000 meters per second. Why? Because particles and solids are closer together, so they pass vibrations along more quickly. Temperature matters too. Warmer air means faster molecules. Sound travels faster in summer than in winter. And yet, despite its speed, sound is delayed enough to notice. Lightning flashes before thunder rumbles. Fireworks bloom silently, then boom seconds later. The delay becomes a kind of distance meter. You can count seconds between lightning and thunder to estimate how far the storm is. Every 3 seconds is about a kilometer. The speed of sound is not a constant limit for all motion, but it's a threshold. Jets that exceed it create sonic booms. Pressure waves piled up like ripples crashing into each other. Sound speed shapes how we hear, how we communicate, how we locate. It is the measure of how fast vibration becomes sensation. Echo and reflection. Call out into a canyon. Wait, and hear your own voice come back. That returning sound is an echo, a reflection of a sound wave, bouncing off a surface and returning to your ears. It's not a recording, it's the same vibration, traveling back after meeting a wall, a mountain, a cliff, or even a hallway. Like light, sound reflects. The smoother and harder the surface, the clearer the reflection. Soft, textured surfaces absorb sound, turning it into heat, dulling its return. That's why concert halls use wood, fabric, or angled panels to control echoes, to shape the way sound behaves. The delay between sound and echo depends on distance. Since sound travels at about 343 meters per second, it takes roughly 0.058 seconds to travel 20 meters to a wall and back. For the echo to feel distinct, there must be at least 0.1 seconds of delay, about 17 meters round trip. In caves, churches, gymnasiums, echoes can linger, repeat, stack on themselves. This stacking is reverberation, not one echo, but many, overlapping, softening, fading. Reflections of sound let us locate things, measure distances, and build sonar. Whales use it. Bats fly by it. Submarines map the ocean floor by echo. Sound reflection is a memory, a reminder that every voice leaves a trace, bouncing gently off the world before fading into silence. Resonance. Why does a singer's voice sometimes shatter glass? Why do bridges sway with the wind? The answer is resonance, the magical, sometimes dangerous amplification of vibration. Every object has a natural frequency, a tone it prefers to vibrate at. Tap a wine glass, and it rings with that frequency. Now play a sound that matches it, and the glass begins to vibrate more, stronger, louder, until it might even break. This happens because energy is transferred efficiently when the frequencies match. Like a swing being pushed in perfect rhythm, every push adds height. That's resonance. In music, resonance gives warmth to instruments. A violin's hollow body, a piano's soundboard, a singer's chest, all resonate to enrich the sound. But resonance can also cause collapse. In 1940, the Tacoma Narrows Bridge twisted and snapped in the wind. Its natural frequency matched the rhythm of the breeze. Resonance is beauty and risk, a reminder that when frequencies align, the world listens and answers. Doppler Effect. Stand by a road as a car passes quickly. You hear the pitch of its engine change, high as it approaches, low as it moves away. This is the Doppler Effect, a shift in frequency caused by motion. When a sound source moves toward you, the waves are compressed. The frequency increases, the pitch rises. As it passes and moves away, the waves stretch out. The frequency decreases, the pitch drops. It's not that the sound changes, it's that you are moving relative to it or it to you. The Doppler effect isn't limited to sound. It happens with all waves, including light. Astronomers use it to measure how fast stars and galaxies are moving. Light from galaxies rushing away appears redder. A redshift. It's how we know the universe is expanding. This effect is a clue, a whisper of motion hidden inside a signal, a change in tone that reveals speed, direction, and distance, even when nothing else can. Standing waves. Pluck a guitar string and watch it vibrate. The wave travels down the string, reflects back, and interferes with itself. The result? A standing wave. A vibration that seems not to travel, but to pulse in place. It has nodes where the string stays still and antinodes where it vibrates most. The pattern is stable, locked in. The wave moves within the string, but its shape doesn't go anywhere. Standing waves happen when waves reflect in just the right way to reinforce and cancel themselves in a repeating pattern. On strings, inside pipes, in your vocal cords. They are the reason instruments produce musical notes. The length and tension of the medium define the frequency, and with it, the pitch. Change the length of a flute tube or the tension in a violin string, and you change the note. Standing waves show us the quiet geometry of vibration, the order within motion, the stillness within sound. Temperature versus heat. Touch a metal railing on a cold morning. It feels icy. Now touch wood beside it. Same air, but not the same feeling. That's the quiet distinction between temperature and heat. Temperature is a measure of how fast the particles in a substance are moving. The more energy they have, the more they jostle, spin, vibrate, and the higher the temperature. But heat is something different. It's energy in motion, the transfer of thermal energy from one object to another. Heat flows. Temperature simply is. When you warm your hands near a fire, heat is flowing from the hot air to your skin. Your body feels warmer because its particles are gaining energy. That's heat. You can have two objects at the same temperature, but very different amounts of heat. A cup of boiling water and a pot full of it. Same temperature, but the pot holds more thermal energy. Temperature is the reading. Heat is the substance. One is the dial, the other is the fuel behind it. The air around you may feel warm or cool, but it's the flow of heat that brings change, that melts ice, boils water, or makes a bed feel cozy on a winter night. Thermal expansion. Heat doesn't just make things hotter, it makes them bigger. When materials warm up, their particles move more, not just faster, farther apart. The result is thermal expansion, the tendency of matter to increase in volume as it gains energy. You've seen it quietly at work, gaps in sidewalks, metal bridges with joints that shift through seasons, a tight jar lid that loosens under warm water, even the sag of power lines on a hot summer day. Solids, liquids, even gases all expand with heat, though not equally. Gases expand dramatically, solids less so, but all carry that secret. Heat creates space. Thermal expansion is used intentionally too. Thermometers rise with temperature. Bimetallic strips curl to control switches. Engine parts are designed to grow slightly during operation. Even sound depends on it. The speed of sound in air changes with temperature because expanding air spreads its particles, letting waves move faster. This expansion is gentle, patient, yet powerful. It bends metal, moves stone, reshapes the world in the slow rhythm of warmth. Heat transfer. Heat always wants to move, from hot to cold, from faster to slower, from the sun to your skin, from your coffee to the air. There are three main ways heat transfers. Conduction is direct contact. Touch a hot spoon, and energy flows from atom to atom, right into your fingers. Metals are good conductors. Their free electrons carry heat quickly. Wood and cloth are not. Convection is motion. Warm fluids, liquids or gases, become less dense, rise, and carry heat with them. Cooler fluid flows in to replace it, creating currents. It's how water boils, how winds blow, how your room heats up in winter. Radiation is pure energy, no matter needed. The sun warms your skin across space. A fire glows with invisible infrared waves. Even your body emits heat through radiation. a constant, gentle light you never see. These methods blend and weave together. A pot on a stove conducts, the water convects, and the flame radiates. A single moment can carry all three. Heat transfer is nature's quiet equalizer. Energy flows until balance is reached, until everything shares the same calm temperature. Specific heat. Why does sand heat up so quickly, but water stays cool under the sun? It's because of specific heat, the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water has a high specific heat. It takes a lot of energy to warm it, and once warm, it holds that heat. That's why oceans stay cool in summer and warm in winter. Why coastal climates feel mild. Why your tea stays warm longer than your plate. Metals, in contrast, have low specific heat. They change temperature quickly, both heating and cooling in short time. Their atoms absorb energy rapidly with little resistance. This concept shapes the weather, controls engines, balances ecosystems. Your body, made mostly of water, benefits from high specific heat too, keeping your temperature steady, your system safe, your warmth consistent even as the world around you shifts. Specific heat is the hidden anchor of temperature, the silent resistance to change. Phase changes. Ice melts, water boils, steam condenses on a window. These are phase changes, the transitions between solid, liquid, and gas. But they aren't just shifts in form. They are deep changes in energy. When a solid melts, energy is absorbed, but temperature doesn't rise. That energy goes into breaking bonds, not speeding up motion. The same is true when boiling water becomes steam. Temperature holds steady until every molecule is free. Freezing and condensation do the reverse. Heat is released as bonds form again. That's why steam can burn. The energy it holds is returned as it condenses onto your skin. There are also more subtle changes. Sublimation, when a solid becomes gas directly, like dry ice disappearing, or deposition, like frost forming from water vapor on a cold window. Phase changes remind us that temperature isn't the whole story. Sometimes energy goes into structure, into relationships between particles, into the shape of matter itself. And in those silent shifts, from ice to water to mist, energy dances behind the scenes, unseen but profound. Ideal gas law. Imagine a balloon gently expanding as you blow into it. The air inside grows in pressure, volume, and energy. But how are these quantities related? The ideal gas law gives us a simple, elegant answer. PV equals nRT. P is pressure. V is volume. N is the number of moles of gas. R is the gas constant. T is temperature in kelvins. This formula is a quiet promise. If you change one part of the gas, its temperature, for example, something else must change too, like its pressure or volume. It's all connected. Heat the gas and molecules move faster. Pressure rises. Let it expand and pressure drops. The law shows how temperature, space, and collisions are tied together. It's not perfect. Real gases deviate from this model under high pressure or extreme cold. But for many conditions, it holds remarkably well, a reliable guide through the invisible world of molecules. The ideal gas law is the heartbeat of weather, engines, stars, a whisper from countless tiny particles, speaking as one. Kinetic theory of gases. What is a gas, really? The kinetic theory sees it not as a smooth fluid, but as countless tiny particles, atoms or molecules, in constant random motion. They bounce, collide, dart, and spin. They strike the walls of their container. And that striking is pressure. Not a force from within, but the sum of millions of tiny impacts. Temperature? That's simply the average kinetic energy of these particles. The hotter the gas, the faster they move. The colder it gets, the slower, until motion almost stops. In this view, a balloon isn't just full of air. It's a crowded dance floor of moving particles, colliding in all directions. The pressure you feel is the rhythm of their motion. The kinetic theory turns warmth into motion, pressure into contact, heat into something you can almost imagine, a quiet buzz of invisible dancers. Even still air is never truly still. There is always motion, always exchange, always energy in motion. First law of thermodynamics. Energy cannot be created. It cannot be destroyed. It can only change. This is the first law of thermodynamics, the law of energy conservation applied to heat and internal energy. It says du equals Q minus W. du is the change in internal energy. Q is the heat added to the system. W is the work done by the system. Add heat to a gas, it can warm up, increase internal energy, or it can expand and do work on its surroundings. But the total energy remains balanced. This law connects heat, work, and internal motion. It tells us that the warmth you feel from a fire isn't created from nothing. It's stored energy being transferred, step by step. Even your own body is a thermodynamic system. Food becomes heat and motion. Muscles do work. Warmth leaves your skin. And still, nothing is lost, only passed along. The first law is quiet and absolute. The universe, it tells us, always keeps the books balanced. Second law of thermodynamics. If the first law says energy is conserved, the second law tells us something deeper. Energy always tends to spread out. Heat flows from hot to cold, never the other way. Left alone, systems become more disordered, more mixed, more uniform. This law gives us direction, a one-way arrow. It's why your coffee cools, why the air never unmixes, why machines need fuel. Because some energy is always lost as heat. It's not that energy disappears, it just becomes less useful, more scattered, harder to collect. You can't unburn a log. You can't unscramble an egg. These aren't just accidents. They're laws written into the physics of the universe. Engines run, but never perfectly. Some energy always slips away. Not lost, just unavailable. That's the tax the universe takes for change. The second law gives time its flow, a silent rule that says, disorder increases. Not in chaos, but in graceful, irreversible drift. Entropy. Entropy is not just disorder, it's the measure of it. The quiet counter of how many ways a system can be arranged without changing its overall appearance. A deck of cards in perfect order has low entropy. Shuffle it, and entropy rises. Every random mix has many more possible arrangements than a neat stack. In physics, entropy tracks how energy becomes less focused, more spread out, more even. High entropy means less ability to do work. The system is balanced but uninspired. The universe moves from low entropy to high. Stars burn and cool. Gases mix. Mountains erode. It's not destruction. It's a kind of peace, the natural tendency of things to settle into equilibrium. Even black holes have entropy. Even time, perhaps, flows because entropy does. Entropy is not chaos. It's a gentle settling, a deep statistical quieting. It reminds us that while energy remains constant, its usefulness slowly fades. And in the end, entropy tells the story of the universe, from fire to stillness, from structure to silence. Static electricity. Touch a doorknob after walking across a carpet and zap. A tiny spark jumps to your hand, surprising, sharp, and gone in a flash. That's static electricity, the quiet buildup of electric charge on a surface, waiting for a path to release. It begins with friction. Rub two materials together, a balloon against hair, shoes on a rug, and electrons shift from one to the other. One object becomes negatively charged, the other positive. Opposites held apart. These charges stay in place, stuck on surfaces until they find a way to balance, often suddenly, like a spark, like a crackling sweater, like lightning jumping from cloud to ground. Static electricity isn't rare, it's everywhere. In dust clinging to screens, in the cling of laundry, in the hush before a storm. And yet for all its sparks and surprises, static electricity is a slow accumulation, a quiet imbalance, a pause before a leap. It shows us that electricity isn't always flowing. Sometimes it waits, silent, stored, ready to move. Electric charge. At the heart of every electrical phenomenon is one simple thing: charge. There are two kinds: Positive and negative. Opposites attract. Likes repel. These forces are the silent language of matter, written into every atom. Protons carry positive charge. Electrons carry negative. Neutrons carry none. They're quiet, neutral. Charge is quantized. It comes in discrete amounts. The smallest unit is the charge of a single electron or proton, and it never comes in halves or fragments. And charge is conserved. It cannot be created or destroyed. It can move, separate, recombine, but the total always stays the same, like a cosmic balance sheet that never forgets a decimal. It may seem abstract, but this is the foundation of everything electric, from a spark to a storm, from a battery to your brain. Charge is invisible but powerful. A tiny imbalance in electrons can light cities, drive machines, shape worlds. All from the quiet tug between positives and negatives. Electric field. Imagine a balloon with static charge. You don't have to touch it to feel it. Just bring your arm near and the hair lifts. That's the electric field, the space around a charged object filled with invisible force. It's not a physical substance, but a region where charge can act. If another charge enters this space, it feels a force. Pulled, pushed, accelerated. Like entering a current you can't see. Every charged object creates its own field, stretching out in all directions. The closer you are, the stronger the field. The more charge, the more powerful the pull or push. Fields are drawn with lines, arrows pointing the way a positive test charge would move. They radiate out from positive charges and curve inward toward negatives. But don't let the lines fool you. The field fills the whole space, quiet, continuous, and waiting. The electric field turns charge from a property into a presence. It lets forces act at a distance. It fills the space between objects with quiet tension. Where there's charge, there's a field. Where there's a field, there's influence, even in stillness. Voltage. Voltage is often described as electric pressure, but really it's something subtler, a difference in electric potential between 2 points. It tells you how much energy per unit of charge can be gained or lost by moving from one point to another. Think of it like height in a landscape. A ball rolls downhill from high to low. Charge does the same, flowing from higher potential to lower. And just like hills create gravity's push, voltage creates the push for electric current. The unit of voltage is the volt, and it's everywhere. Batteries have voltage, outlets, lightning bolts, even your nerves. But voltage alone doesn't create flow. You also need a path. Without a circuit, the pressure builds, but nothing moves. Still, voltage sets the stage. It's the difference that matters, the reason current flows, the motivation behind the movement. Where there's voltage, there's the possibility of motion, a quiet readiness, a stored desire to flow. Current. Now imagine a wire connecting 2 points with different voltage. The path is open. The potential is there, and now the charges begin to move. This is electric current, the flow of electric charge through a conductor. Usually it's electrons that move, drifting slowly but steadily through the metal. The amount of current depends on how much charge passes a point per second. Its unit is the ampere, or amp. 1 amp means 1 coulomb of charge flows by every second. Current flows from higher to lower voltage, though electrons actually move in the opposite direction. In physics, we define conventional current as the flow of positive charge, a tradition from before electrons were discovered. Current can be direct DC, always flowing the same way, like in batteries. Or alternating, AC, changing direction many times per second, like in household electricity. Electric current powers everything: light bulbs, computers, motors, your heart. It is the river that runs through the world of circuits, a gentle stream of invisible particles, guided by potential, shaped by resistance, energized by voltage. Resistance and Ohm's law. Electricity wants to flow, but not everything lets it pass easily. Materials push back. This opposition is called resistance. It's a quiet kind of friction, a slowing down of current as electrons bump into atoms, lose energy, warm things up. Metals like copper have low resistance. Electrons slip through easily. Rubber or glass resist strongly. They're insulators, blocking the flow almost completely. The relationship between voltage, current, and resistance is given by a simple rule. Ohm's law, V equals IR, V is voltage, I is current, R is resistance. Increase the voltage, more current flows. Increase the resistance, the current slows down. This law is the heartbeat of every circuit, from light bulbs to laptops. It tells us how energy moves, how it's divided, how it's consumed. And resistance isn't always bad. It lets us control current, manage power, protect components. A resistor in a circuit is like a narrow gate. It shapes the flow without stopping it. Ohm's law is simple, but in its simplicity lies the key to almost all of electrical engineering. Simple circuits. A battery, a wire, and a light bulb. Connect them, and the bulb glows. Energy flows. This is a simple circuit. A closed loop that allows electric current to move from one point to another and back again. The battery provides voltage, a difference in potential. The wire carries charge. The bulb resists, glows, and releases energy as light and heat. Then the current returns to the battery, and the loop continues. For a circuit to work, it must be closed. A complete path. Break the loop, and the flow stops. Simple circuits can be arranged in two ways. Series. Components are connected end-to-end. The same current flows through each. Parallel. Components are connected side by side. Each gets full voltage, and current splits between them. Circuits can be as basic as a flashlight or as complex as a computer chip. But the core idea never changes. A loop, a source, a load. In that loop, energy moves. Quietly, invisibly, but with purpose. Powering everything from ideas to industries. Magnetic fields. Rub a magnet across a needle and it aligns, pointing north. Invisible lines seem to pull it into place. That invisible pull is a magnetic field, a region where certain materials, like iron, feel a force. Every magnet has two poles, north and south. Opposites attract, likes repel. Around the magnet, field lines form loops. Out from the north pole back into the south. Always circling, always connected. But where does the magnetism come from? At the atomic level, electrons spin and orbit, creating tiny currents. In most materials, these cancel out. But in magnets, the effects add up. Billions of atomic fields aligned, working together. Earth itself is a giant magnet, with a field stretching far into space. It protects us from solar wind, guides compasses, shapes auroras. Magnetic fields can't be seen, but they can be felt as tug, twist, or torque. They surround wires with current, shape charged particles, and hold secrets in every atom. They are the silent companions to electricity, always near, always curved, always reaching. Electromagnetism. Electricity and magnetism may seem like separate forces, but they are deeply connected. Together, they form electromagnetism. When current flows through a wire, it creates a magnetic field around it. This was discovered in 1820, and it changed everything. Wrap that wire into a coil, and the field strengthens. Insert iron inside, and it becomes an electromagnet, a controllable magnet, turned on and off with current. It can lift scrap metal, run speakers, or power MRI machines. Electromagnetism is reversible too. Move a magnet near a wire, and current flows. This is the basis of generators, microphones, wind turbines. Changing magnetic fields create electric fields. Changing electric fields create magnetic fields. This interplay is described by Maxwell's equations. 4 elegant rules that unify light, radio waves, electricity, and magnetism. Electromagnetism is more than a force. It's a dance between motion and field, charge and space. It governs light, atoms, nerves, the sun. In this force, 2 worlds become one. Electromagnetic induction. Take a loop of wire. Move a magnet through it. Suddenly a current appears. No battery, no spark, just motion. This is electromagnetic induction, the process of generating electric current from a changing magnetic field. Discovered by Michael Faraday in 1831, it showed that magnetism could create electricity. A moving field produces voltage. Faster changes create stronger effects. This is how generators work. by spinning coils near magnets, turning motion into energy. Induction obeys Faraday's law. The induced voltage in a loop is proportional to the rate of change of magnetic flux through it. It also obeys Lenz's law. The induced current always opposes the change that created it, a kind of resistance, a balancing act. This principle powers our world. Every power plant, from coal to solar to nuclear, uses induction to generate electricity. It turns wind into watts, waterfalls into current, rotation into light. Induction is quiet, elegant, and foundational. It closes the loop between magnetism and current and opens the door to modern life. Nature of light. What is light? For centuries, no one could agree. Was it a wave rippling through some invisible ether? Or was it a stream of particles, fired like tiny arrows from stars? The answer is both. Light is an electromagnetic wave, a self-sustaining ripple of electric and magnetic fields, traveling through space at 300,000 kilometers per second. It needs no medium. It moves through the vacuum of space from sun to earth in just over 8 minutes. But light is also quantized, made of discrete packets of energy called photons. These are not particles with mass, but bundles of energy that behave like particles in some situations, like when they strike metal or trigger a retinal cell in your eye. This dual nature, wave and particle, is called wave-particle duality. It's not contradiction, but complement, a whisper from the quantum world that says, reality is more than it seems. Light is how we see, how we know, how we measure the stars. It's both information and energy, the messenger of the universe. Reflection and refraction. Light travels in straight lines until it meets something new. When it hits a surface, it may reflect, bouncing off like a ball striking a wall. The angle it arrives at equals the angle it leaves, the law of reflection. This is how mirrors work, how you see yourself, how light bounces across a room. But sometimes light passes through and bends. This bending is refraction. When light enters a new material, water, glass, air, its speed changes. And with that, its direction shifts. Like a car crossing from pavement to mud at an angle, one side slows down first, turning the whole. This is why a straw in a glass looks bent, why pools seem shallower than they are, why lenses can focus light or spread it. Reflection and refraction are simple rules, but they give rise to brilliance, from rainbows to telescopes, illusions to lenses. They remind us that light isn't just about brightness, it's about behavior. Lenses and mirrors. With just the right shape, a piece of glass can bend light and change the way we see. Lenses are curved pieces of transparent material that refract light. A convex lens brings rays together, focusing them at a point, like a magnifying glass. A concave lens spreads them apart, softening the image. Lenses are in cameras, glasses, microscopes, and your eyes. They let us read, see stars, study cells. They let us bring far things near. Mirrors, meanwhile, work by reflection. A flat mirror shows a reversed image. A concave mirror can focus light to a point, bright and hot. A convex mirror spreads the view, letting you see around corners. Combine mirrors and lenses and you can build almost anything. Telescopes to explore galaxies, projectors to fill a screen, fiber optics to guide light through hair-thin strands. These tools don't just show the world, they shape what's visible. They extend your vision beyond the surface, into the hidden, the distant, the small. Optical illusions. Sometimes what we see is not what is. Optical illusions happen when light behaves one way and our brains expect another. They reveal not flaws in vision, but the shortcuts of perception. Guesses the mind makes, often too fast. A line appears bent in water, but it isn't. A flat image seems to move. Parallel lines look like they're bowing. A color looks darker in one shadow, lighter in another. Our brains process light, shadow, context, and expectation all at once. They fill in gaps. They assume lighting, motion, continuity. Illusions use these assumptions to trick us, not maliciously, but playfully. They reveal that sight is not passive, it's an interpretation. Some illusions are rooted in physics, like mirages caused by light bending in hot air. Others are psychological, shapes and colors that confuse the brain's filters. In every case, they remind us, the world we see is not just out there, it's also inside us. Color in the visible spectrum. White light isn't plain, it's many colors in one. Pass it through a prism and it splits into red, orange, yellow, green, blue, indigo, violet, a rainbow in a beam. This is the visible spectrum, the narrow band of electromagnetic waves that human eyes can detect. Wavelengths from about 400 to 700 nanometers. Red has the longest wavelength, gentle, low-energy waves. Violet has the shortest, sharper, more energetic. Beyond violet is ultraviolet. Beyond red, infrared. We can't see them, but they're still light, just out of reach. Color happens because different materials absorb or reflect certain wavelengths. A leaf absorbs red and blue and reflects green, so we see it as green. Some animals see more than we do. Bees see ultraviolet. Snakes detect infrared. Our world is a slice of a much wider spectrum. Color is perception, a story your brain tells about light. And in every hue, there's a hidden frequency, a hidden wave, a hidden energy. Diffraction. Light travels in straight lines until it doesn't. When light passes through a narrow opening or edges around an object, it bends and spreads out. This is diffraction, the soft unraveling of light around barriers. It's most noticeable when the gap is small, close to the light's own wavelength. Shine a laser through a slit, and you won't see a simple beam. You'll see ripples, fringes, interference patterns. This bending isn't because of reflection or refraction. It's the wave nature of light expressing itself. Waves, after all, don't like to be constrained. They spread. You've seen diffraction without realizing it. The shimmering colors on a CD, the glow around a shadow, the rainbow corona around a bright light. Even sound diffracts. That's why you can hear someone around a corner. But light's shorter wavelengths mean it diffracts less. Only when openings are tiny. Diffraction shows us that light isn't just a path. It's a pattern, and edges don't block it. They shape it. Polarization. Most light waves vibrate in many directions, up and down, side to side, diagonally. But when all the waves align in a single direction, we call that light polarized. Polarization is the filtering of light's electric field into one plane. You can polarize light by passing it through special filters, like polarized sunglasses. These block glare by absorbing horizontally vibrating light, which is often reflected from surfaces like water or glass. Natural light is unpolarized, a mix of all directions. But once filtered, it becomes ordered, simplified. This doesn't change its color or brightness much, just its geometry. Polarization isn't just for sunglasses. It's used in 3D movies, LCD screens, optical communication, even in studying stress in materials. Some animals, like bees and cuttlefish, can see polarization, giving them a dimension of vision we lack. To us, it's invisible. But polarization reminds us, even light has orientation. Even brightness can have structure. Interference. When two waves of light meet, they don't clash, they combine. This is interference, and it can be constructive or destructive. If two waves arrive in sync, peak with peak, valley with valley, they build each other up. But if they arrive out of sync, peak with valley, they cancel out. The result is not chaos, but a pattern, bright and dark bands rippling across space. You can see interference in soap bubbles, oil slicks, the iridescent wings of insects. Thin films create layers where light reflects from multiple surfaces, overlapping just enough to interfere. This phenomenon was famously shown in the double-slit experiment. Shine light through two narrow slits, and it creates not two spots, but a whole spread of fringes. This was one of the first proofs that light behaves like a wave. Interference shows that light isn't solitary. It interacts. It layers. It harmonizes, or silences, with itself. A quiet reminder that even in light, patterns come from meeting. Speed of light. Light is fast, Not just fast, the fastest thing in the universe. In a vacuum, it travels at exactly 299,792,458 meters per second, nearly 300,000 kilometers per second, or about 7.5 times around Earth in 1 second. Nothing with mass can reach this speed. Light isn't just fast. It defines what speed is. It's the cosmic speed limit. But light slows down slightly in materials. In water, it's slower. In glass, slower still. That's why refraction happens. The bending of light as its speed shifts. The speed of light is more than a number. It links time and space. In Einstein's theory of relativity, it anchors reality. No information, no signal, no cause can travel faster. It also lets us see the past. Light from the moon is 1.3 seconds old. From the sun, 8 minutes. From distant stars, thousands, even millions of years. We don't see them as they are, but as they were. The speed of light connects motion, vision, time, and distance, a silent ruler stretching across the cosmos. Dual nature of light. Is light a wave or a particle? The answer is strange and beautiful, both. Light behaves like a wave when it bends, diffracts, or interferes. But in other cases, it acts like a stream of photons, tiny, massless packets of energy. In the photoelectric effect, for instance, light shining on a metal can knock out electrons, but only if its frequency is high enough. This only makes sense if light arrives in quanta, with each photon carrying a specific amount of energy. This discovery helped launch quantum physics, and even won Einstein a Nobel Prize. Wave-particle duality isn't just a weird trick, it's a deep truth. Light can't be fully explained as one thing. It behaves differently depending on how we observe it. Not just light, all particles have this duality. Even electrons can show interference patterns, even atoms, even us in theory. The dual nature of light tells us something profound. Reality is not fixed, it's contextual. It depends on how we look. The photoelectric effect. Imagine shining a light on a metal surface, and suddenly electrons leap out. That's the photoelectric effect, a discovery that changed physics forever. Scientists once thought that increasing the light's intensity would always release more electrons, but it didn't. If the light's frequency was too low, nothing happened, no matter how bright the light was. But when the frequency passed a certain threshold, even dim light could knock electrons free. Why? Because light isn't just a wave. It comes in packets called photons. Each photon has energy proportional to its frequency. Only photons above a certain energy can kick electrons loose. This experiment couldn't be explained by classical physics. It revealed the quantum nature of light and confirmed that energy is quantized. Einstein explained it in 1905, winning the Nobel Prize. The photoelectric effect is now the basis for solar panels, light sensors, and quantum devices. It proved that light delivers energy one photon at a time, like tiny messengers knocking at matter's door. Planck's constant. To understand the quantum world, we need a new kind of constant, one that connects energy and frequency. That constant is Planck's constant, each approximately 6.626 times 10 to the negative 34th power joule seconds. It's a very small number, but its meaning is enormous. Planck's constant tells us how quantized the universe really is. According to the formula, E equals h times F. The energy, E, of a photon is equal to its frequency, F, multiplied by Planck's constant. This means energy doesn't flow continuously. It comes in discrete packets. A photon of red light has less energy than a photon of blue light, not because it's brighter, but because its frequency is higher. Planck's constant sets the scale of the quantum world. It marks the border between classical physics and quantum behavior. At large scales, h is so small that it disappears into the background. But at atomic scales, it rules everything. It's the rhythm of the quantum beat, the grain of the universe's fabric. Quantum versus classical. Drop a ball and it falls. Predictable, definite. But in the quantum world, particles don't follow such clean rules. Classical physics describes objects we see every day. Planets, cars, baseballs. It assumes that things have definite properties: position, velocity, energy, all measurable, all calculable. But quantum physics deals with the tiny atoms, electrons, photons. And here, certainty fades. Particles behave like waves. Positions blur into probabilities. Actions happen in quanta, not continuous flows. Observing something changes it. In classical mechanics, you can know everything, if you have enough information. In quantum mechanics, some things are unknowable by nature. Classical physics is smooth and certain. Quantum physics is granular and probabilistic. Yet both are true and in their own domains. The world of people follows Newton. The world of particles dances to Planck. Between them is a strange boundary, and at that edge the universe becomes less like a machine and more like a mystery. Wave-particle duality. In the quantum world, things are not just one thing. Light is a wave and spreading, diffracting, interfering. But it's also a particle, arriving in discrete, countable photons. Wave-particle duality says this isn't just about light. Matter behaves this way too. Electrons, when not observed, move like waves. They can interfere with themselves, diffract through slits, form patterns on screens, just like light. But when measured, they appear as single points. This duality means particles have wavelengths, described by the de Broglie equation, E equals h divided by p, where lambda is wavelength, h is Planck's constant, and p is momentum. For tiny particles, the wavelength is large enough to observe. For people or planets, the wavelength is so small it's irrelevant. Wave-particle duality doesn't mean particles are part wave, part particle. It means they are neither and both, depending on how we interact with them. Reality is not fixed, it's participatory, and in that uncertainty is wonder. The uncertainty principle. Try to measure an electron's position. Exactly. Now try to measure its momentum. Exactly. You can't do both at the same time. This is the Heisenberg uncertainty principle. The more precisely you know one property, the less precisely you can know the other. It's not a limitation of tools, it's a fundamental property of quantum systems. At small scales, particles don't have exact positions and velocities. They exist in probability clouds. Blurred, spread out possibilities. You can find where they probably are, but not precisely. This uncertainty is not an error. It's baked into the fabric of nature. It leads to strange consequences. Particles tunneling through barriers, atoms never sitting still, energy borrowing itself for brief moments. The uncertainty principle doesn't say we know too little. It says the universe, at its heart, is not fully knowable. It breathes uncertainty into every particle, and in doing so, makes the universe alive with possibility. Quantum tunneling. Imagine a hill. In classical physics, a ball without enough energy can't get over it. But in quantum mechanics, it might simply pass through. This is quantum tunneling, the eerie phenomenon where particles appear on the other side of a barrier they shouldn't be able to cross. It's not magic, it's probability. In quantum mechanics, particles are described by wave functions, smooth curves that extend beyond where we expect the particle to be. Even if energy is too low, the wave doesn't vanish instantly, it fades. And sometimes on the far side of a barrier, it still exists, meaning there's a chance the particle might appear there. Tunneling isn't rare. It powers nuclear fusion in stars, allowing protons to overcome repulsion and combine. It's used in scanning tunneling microscopes, letting us image atoms. It even plays a role in radioactive decay as particles escape atomic nuclei. Quantum tunneling says, barriers are not absolute. Walls may be solid, but reality is soft. Atomic orbitals. Electrons don't orbit atoms like planets around stars. That picture is too simple. Instead, they exist in orbitals, three-dimensional regions where there's a high probability of finding them. These orbitals aren't paths, they're clouds, patterns, standing waves in space. Each orbital is defined by a set of quantum numbers, rules that govern shape, orientation, and energy level. The s orbital is spherical, a soft, centered cloud. The p orbitals look like dumbbells, oriented along different axes. D and f orbitals are more complex, flower-like, multi-lobed. Electrons don't sit in fixed spots. They exist as possibilities, distributed across these orbitals in elegant, rule-bound ways. Orbitals explain why elements behave as they do, how they bond, how they glow, how they interact. They're the architecture of chemistry, the quiet architecture of the periodic table. In every atom, orbitals hum like invisible harmonies, the shape of where an electron might be. The Standard Model. What is everything made of? The Standard Model of particle physics is our best answer, a framework that describes the most fundamental particles and forces of the universe. It includes quarks, which make up protons and neutrons, leptons like the electron and neutrinos, gauge bosons which carry forces like photons and gluons, and the Higgs boson which gives particles mass. There are 6 types of quarks and 6 leptons, arranged in families, from the familiar, up-down electron, to the exotic, top-bottom tau. The model describes 3 fundamental forces: electromagnetic via photons, weak nuclear via W and Z bosons, strong nuclear via gluons. Gravity, strangely, is not included. Everything you see, stars, trees, breath, light, comes from combinations of just a few particles dancing through quantum fields. The Standard Model is astonishingly accurate, yet incomplete. It doesn't explain gravity, or dark matter, or why particles have the masses they do. Still, it's our closest glimpse at the scaffolding of reality. Antimatter. For every particle we know, there exists an opposite. Antimatter is like a mirror reflection of normal matter. The positron is the electron's twin, with the same mass but positive charge. Antiprotons and antineutrons mirror the particles inside atoms. When matter and antimatter meet, they annihilate, converting entirely into energy, usually gamma rays. This makes antimatter extremely powerful and very dangerous in large amounts. But where is it? In theory, the Big Bang should have produced equal amounts of matter and antimatter, yet our universe is made almost entirely of matter. This imbalance is one of the deepest mysteries in physics. Antimatter isn't science fiction. We create it in particle accelerators. PET scans in hospitals use positrons. It's rare but real. And if we could ever contain and control it safely, it could become the most energy-dense fuel imaginable. Antimatter shows us that for every what is, there may be an anti-what could be. Quantum entanglement. 2 particles interact, then separate, and somehow measuring one instantly affects the other, even across vast distances. This is quantum entanglement, one of the strangest and most beautiful features of quantum mechanics. Entangled particles are linked not by force, but by shared quantum state. Their properties, spin, polarization, position, become connected in such a way that one can't be described without the other. Measure one, and the other's state is instantly determined, no matter how far apart they are. Einstein called this spooky action at a distance, because it seemed to violate the speed of light, but it doesn't send information faster than light. It simply reflects that quantum systems are non-local, parts of a whole even when separated. Entanglement isn't just weird, it's useful. It powers quantum cryptography, quantum teleportation, and forms the heart of future quantum computers. It's a quiet reminder. The universe may be more connected than it seems, that in the quantum world, separation is never complete. Special relativity. In 1905, Albert Einstein proposed something that changed everything. The laws of physics are the same for all inertial observers, those moving at constant speed, and the speed of light is constant no matter how fast you move. These 2 postulates led to a theory called special relativity, and with it, space and time were no longer separate. They became one, space-time. In this new view, moving clocks tick slower, moving objects become shorter, and events that seem simultaneous in one frame may not be in another. Nothing can travel faster than light, and the faster you move, the more reality bends around you. Special relativity is not about what you see, but what you measure. It's not illusion. It's the structure of the universe, revealed through speed. And even though we don't notice it at walking pace, at near-light speed, everything changes. Space shrinks, time stretches, mass grows. and the universe begins to hum with strange, beautiful symmetry. Length contraction. Imagine you're flying near the speed of light. To someone watching from Earth, your spaceship looks shortened, compressed in the direction of motion. This is length contraction, one of the many strange predictions of special relativity. Objects in motion appear shorter along their direction of travel, according to observers at rest. It's not a trick or distortion, it's real, it's measurable. But it only becomes noticeable at speeds close to light. The faster you go, the more space shrinks in your direction of motion. Yet on board the ship, you feel nothing unusual. The cabin stays the same. Time flows normally, but to others your world is thinner, more compressed. This isn't just theory. It's observed in particle accelerators, where fast-moving particles live longer and travel farther than they should, because in their frame, distance is shorter. Length contraction reminds us, space isn't absolute. It's part of a dynamic fabric, one that stretches and compresses depending on how you move. Mass-energy equivalence. Perhaps the most famous equation in physics, E equals mc squared. Energy equals mass times the speed of light squared. This elegant formula tells us something profound. Mass and energy are the same thing, two forms of the same underlying substance. A small amount of mass can become an enormous amount of energy because c squared, the speed of light squared, is such a huge number. This principle powers the sun, where mass is turned into energy through nuclear fusion. It fuels nuclear reactors, and sadly, nuclear weapons too. But it also reveals something deeper. Mass is not just stuff, it is frozen energy. When a particle moves faster, its energy increases, and so does its relativistic mass. Even light, though massless, carries momentum and energy. In a sense, everything we see, every stone, star, and cell, is a knot of energy, shaped by space, bound by mass. Mass is energy, waiting to move. General relativity. Special relativity dealt with motion. But what about gravity? In 1915, Einstein completed his masterpiece, General Relativity, a new theory of gravity not as a force, but as geometry. Mass and energy curve space-time. Objects, and even light, follow the straightest possible paths through this curved geometry. Imagine a heavy ball on a stretched rubber sheet. It dips the surface. A smaller ball rolls toward it, not because it's pulled, but because the sheet is bent. This is how planets orbit stars, how light bends around galaxies, how time slows near black holes. General relativity predicted black holes, gravitational waves, and the expansion of the universe. A century later, these predictions are still being confirmed. And it all starts with a quiet idea. Gravity is not a force pulling down, it is space curving in. Mass tells space-time how to curve, space-time tells matter how to move. Gravitational time dilation. Time is not a constant tick-tock across the universe. It bends, it stretches, it slows, under the weight of gravity. This is gravitational time dilation, a consequence of general relativity. The stronger the gravitational field, the slower time flows. Near a massive object, so like a black hole, time can slow to a crawl or nearly stop. Clocks on satellites tick faster than those on Earth's surface because they're farther from Earth's gravity. We correct for this every day in GPS systems, or else our maps and locations would drift off. This isn't science fiction. It's measurable, precise, and woven into our technology. Gravitational time dilation means that time is not universal. There is no master clock, no shared now. Instead, time depends on where you are and how strong the gravity is around you. And so, on a cosmic level, your heartbeat is relative. Black holes. A black hole is not just a thing, it's a place where space and time collapse. When a massive star runs out of fuel, it can collapse under its own gravity. The result, a region so dense, with gravity so strong that not even light can escape. This is a black hole. At its center lies a point called the singularity, where density becomes infinite and the known laws of physics break down. Around it, a boundary, the event horizon. Once crossed, nothing returns. Black holes come in sizes. some just a few kilometers across, others millions of times more massive than the Sun. We now know that supermassive black holes sit at the heart of most galaxies, including our own. But black holes aren't just cosmic vacuum cleaners. They shape galaxies, warp time, and may even hold clues to quantum gravity. Approach one, and time slows. Matter stretches, light curves, and yet they're silent, invisible, detected only by what disappears into them or what orbits their darkness. Wormholes. Imagine folding a piece of paper, two distant points touching. Now imagine cutting a hole between them. This is the idea of a wormhole, a hypothetical tunnel through space-time, connecting distant regions like shortcuts through the universe. Predicted by solutions to Einstein's equations, wormholes are mathematically possible, but remain speculative. We've never observed one, and they might require exotic matter with negative energy to stay open. Still, they stir the imagination. Could we travel across galaxies in moments? Could the universe be filled with unseen bridges, ancient paths folded in time? Some even wonder if wormholes connect not just places, but times. If the universe is threaded with links across centuries and light years. For now, they remain theory, but a theory born from real physics. A whisper that perhaps space is not as far apart as it seems. Expansion of the universe. In every direction we look, galaxies are moving away from us. Not because we're at the center, but because space itself is expanding. This discovery, confirmed in the 1920s by Edwin Hubble, changed everything. It meant the universe had a beginning, a moment when it was smaller, hotter, denser. That moment is called the Big Bang. Not an explosion in space, but an explosion of space. Since then, the universe has been stretching, not like objects flying apart, but like the fabric of space growing between them. And it's not slowing down. In fact, it's accelerating. Distant galaxies recede faster and faster. The farther they are, the faster they flee. Eventually, many may drift so far they vanish from view, beyond the edge of light. Expansion isn't just motion, it's creation. Space, time, distance, all growing. And we ride this silent wave, unaware, inside a cosmos that's getting bigger by the second. Cosmic microwave background. Long ago, the universe was not dark and empty. It was hot, dense, glowing with light, a searing plasma of particles and radiation. Then about 380,000 years after the Big Bang, the universe cooled just enough for atoms to form. Light could finally travel freely, and that light is still here. It's called the Cosmic Microwave Background, CMB, the oldest light in the universe. Not visible to the eye, but detectable as a faint microwave glow in every direction. First discovered in 1965, the CMB is like a baby photo of the cosmos, a frozen echo of its first breath. It's not uniform. It has tiny temperature ripples, clues about the seeds of galaxies, the shape of space, and the fate of everything. Today we measure it with exquisite precision. It confirms the Big Bang, maps the curvature of space, and tells us how the universe evolved. In this ancient light, the universe still whispers its beginning. Dark matter and dark energy. When we observe galaxies, we find something strange. They spin too fast. They should fly apart, but they don't. Something invisible must be holding them together. We call it dark matter, a mysterious form of mass that doesn't emit, absorb, or reflect light. It doesn't interact with us, only with gravity. It forms halos around galaxies, shapes the large-scale structure of the cosmos, and makes up about 27% of the universe. But that's not all. In the 1990s, scientists discovered that the expansion of the universe is accelerating. Some unknown force is pushing space apart. We call it dark energy, and it accounts for nearly 70% of the cosmos. That means everything we can see, stars, planets, atoms, makes up less than 5% of reality. The rest is unseen, unfelt, unknown. We name it, but we don't understand it. Dark matter and dark energy are the hidden threads of the universe. Silent, invisible, and everywhere. Quantum field theory. What is a particle? Not a tiny ball, not a dot. In quantum field theory, QFT, every particle is an excitation in a field, like a ripple in an invisible ocean that fills all of space. There is a field for each kind of particle: the electron field, the quark field, the photon field. Even in empty space, these fields are there, silent until disturbed. When a field vibrates in a certain way, it creates a particle. So an electron is not a thing floating in space. It is space shaped into form by its field. QFT merges quantum mechanics with special relativity, and it's the foundation of the Standard Model. It predicts how particles interact, decay, and transform. It's also a theory of probabilities, not certainties. Fields can interfere, cancel, enhance, and their interactions play out in a language of complex math: elegant, abstract, precise. At this level, matter dissolves into energy. Energy dissolves into information. And everything you've ever touched is just a pattern in a field. Virtual particles. In the vacuum of space, as supposedly empty, particles are constantly appearing and disappearing. These are virtual particles. They aren't directly observable. They don't last long enough to be detected. But they're real in the sense that they affect the world. They appear in calculations. They help explain forces. They leave footprints in tiny shifts in electron energy, in the forces between particles, in the fabric of the vacuum itself. Virtual particles pop into existence by borrowing energy, just for a moment, then vanish in perfect respect for the uncertainty principle. They mediate forces: photons for electromagnetic force, gluons for the strong force, W and Z bosons for the weak force. Without them, the universe would be static, disconnected. But with them, particles talk, repel, attract. They are the whispers of the quantum vacuum, the invisible glue that holds interactions together. Even nothing is something. Higgs boson. Why do some particles have mass while others do not? The answer lies in the Higgs field, an invisible field that permeates all of space. As particles move through this field, some interact more strongly than others. That interaction slows them down and gives them mass, like swimmers moving through honey. The Higgs boson is the particle associated with this field. It's the ripple that confirms the field exists. For decades, it was predicted but never seen. Then in 2012, scientists at CERN's Large Hadron Collider announced the Higgs had been found. It was the last missing piece of the Standard Model, and one of the greatest discoveries in modern physics. The Higgs doesn't just explain mass, it confirms that fields shape what's real. That mass isn't an inherent thing, it's a result of interaction. In a world of fields, the Higgs gives weight to being. Superconductivity. At everyday temperatures, electric currents face resistance, friction in the wires. Energy is lost as heat, but cool some materials below a critical temperature, and something remarkable happens. Resistance drops to zero. Electricity flows forever, without loss. This is superconductivity. Electrons, normally scattered by atoms, begin to pair up into delicate units called Cooper pairs. These pairs move in harmony, immune to the bumps and barriers that usually cause resistance. Superconductors can do amazing things: create powerful magnetic fields, levitate magnets, or float above them, enable ultrasensitive sensors and efficient energy transmission. And in the heart of MRI machines, particle accelerators, and future technologies, superconductivity is quietly at work. It's a reminder that temperature reveals hidden phases of matter, and that at low enough energies, quantum behaviors emerge at macroscopic scales. Silence the thermal noise, and nature begins to sing in harmony. Symmetry and conservation laws. In physics, symmetry is not just beauty, it's law. A system that stays the same under certain transformations has symmetry, and each symmetry implies a conservation law, a deep, unbreakable rule of nature. This idea is formalized in Noether's theorem. If the laws of physics don't change over time, energy is conserved. If they're the same in every place, momentum is conserved. If they're the same in every direction, angular momentum is conserved. Symmetry leads to order. It explains why energy doesn't disappear, why objects spin steadily, why motion follows smooth arcs. But symmetry can also be broken, and when it is, new forces arise. The early universe may have had perfect symmetry, and its breaking gave rise to mass, to charge, to structure. The universe at its heart is a balance between symmetry and spontaneity, a place where conservation laws keep time steady, but also where subtle imbalances give rise to everything. The arrow of time. Why does time flow only forward? In the microscopic world of physics, the fundamental laws are time-symmetric. They work just as well in reverse. An equation doesn't care if you run time backward. Yet in life, we remember the past, not the future. Eggs break, but don't unbreak. We grow older, never younger. This is the arrow of time, the direction time seems to move. And it comes from one deep idea: entropy. Entropy is the measure of disorder. According to the second law of thermodynamics, entropy tends to increase. Systems evolve from order to disorder, from low entropy to high. And so, time points in the direction of increasing entropy. That's why we see cause before effect, not the other way around. The universe began in a low entropy state, smooth, hot, dense. Since then, it's been spreading out, cooling, mixing. And we too are caught in that flow, living moments that never repeat in a cosmos slowly winding down. Time doesn't just pass, it unfolds, leaving behind a trail of increasing complexity and memory. Grand unified theories. In the early universe, moments after the Big Bang, all the forces of nature may have been one, a single superforce, undivided. As the universe cooled, this force split, like crystal cracking as it freezes, into the fundamental forces we know today: gravity, electromagnetism, strong and weak nuclear. Grand unified theories, GUTS, attempt to merge the strong, weak, and electromagnetic forces into a single framework, a deeper symmetry beneath what we observe. These theories suggest that protons might eventually decay, and that all matter is woven from the same fundamental threads. While unproven, GUTS offer a vision that the diversity of particles and forces is a kind of broken unity, like a rainbow from white light. The search for unification continues in particle accelerators, in neutrino detectors, and in the minds of physicists who dream of restoring the cosmos to its original wholeness. Before the forces separated, there was one law: string theory. What if particles aren't points but vibrating strings? Tiny loops or lines, oscillating at different frequencies, and those vibrations determine the properties we observe: mass, charge, spin. This is string theory. In this framework, all particles are just modes of vibration of fundamental strings, like notes played on the same instrument. But strings don't work in just 3 dimensions of space. They need 10 or 11 dimensions, most of them curled up so tightly we can't perceive them. String theory also naturally includes gravity, which has long resisted being unified with quantum mechanics. It's elegant, symmetrical, mysterious, and unproven. There are no experimental confirmations yet, but string theory offers a candidate for the elusive theory of everything: one framework, one language for all phenomena. In the beginning was the string, and the string was vibration, and the vibration became the world. Multiverse hypothesis. What if our universe isn't the only one? The multiverse hypothesis suggests that our cosmos may be just one of many, perhaps infinitely many, each with different laws, constants, histories. Some ideas arise from cosmic inflation, where rapid expansion could create countless bubble universes. Others from string theory, which allows for many stable configurations. Still others from quantum mechanics, where every possible outcome may branch into its own universe. In some, stars may never form. In others, gravity could be stronger, or time could run differently. In one, you might not exist. In another, you already do. We may never detect these other universes, but if the laws of nature permit them, are we not already part of a greater reality? The multiverse doesn't shrink our place, it expands it, showing that the cosmos may be more vast, varied, and alive than we ever imagined. Theory of everything. For centuries, we've tried to explain the world through fewer and fewer rules. From Newton's mechanics, to Maxwell's electromagnetism, to Einstein's relativity, to the standard model of particles. Each step brought us closer to unity. But one great riddle remains. Gravity doesn't fit with quantum mechanics. Two beautiful theories are both true, yet they resist being combined. The dream is a theory of everything, a single, consistent framework that explains all fundamental forces, all particles, all interactions. One equation, one story. String theory is one candidate. So is loop quantum gravity, or even ideas not yet imagined. Such a theory would not just unify forces, it would reveal the deepest symmetries of reality. Why the universe exists as it does, why it permits life, why anything happens at all. And perhaps in that theory, we would find that matter, energy, space, time are all just expressions of a deeper truth, one that binds the cosmos together in silence and symmetry, a final law woven in whispers. What is reality made of? We often imagine the universe is made of things, atoms, particles, stuff, but modern physics tells a different story. At its most fundamental, reality may not be made of matter at all, but of fields, energy, and even information. Particles are just ripples in fields. Mass is a form of energy. Space and time themselves may be emergent. Not primary ingredients, but patterns that arise from something deeper. Some physicists now suggest the universe is not built from substance, but from relationships, correlations, probabilities, and interactions. A particle has no identity on its own. It's defined by how it interacts. So perhaps reality isn't made of things, but of processes. Not objects, but events. Not solidity, but structure. What we call the physical world may be a kind of ongoing calculation, a cosmic unfolding governed by rules, rhythms, and elegant math. Reality, in the end, may be more like a story than a sculpture. The nature of time. What is time? We feel it, we measure it, we live within it, but we don't really understand it. Is time something that flows, or just a way to describe change? In physics, time is a coordinate, like space. Events have locations in space-time, but we experience something more, a now, a before, and after. Some theories suggest that time doesn't flow, that past, present, and future all exist at once, in a block universe. We move through it like reading pages in a book. Others propose that time emerges, from quantum entanglement, from thermodynamics, from complexity. We know that time is relative, it flows differently depending on speed and gravity, it slows near black holes, it stretches in motion. But what is it really? Is it a dimension, a direction, an illusion? Perhaps time is not something that passes, but something we create, moment by moment, as we experience the unfolding of reality. Can time run backward if the laws of physics don't care about direction? Why does time only move forward? In theory, many physical processes are time reversible. If you filmed them and played them backward, the math would still work. Yet in real life, we never see unmixing, unbreaking, unburning. This one-way flow is called the arrow of time, and it emerges from the second law of thermodynamics. Entropy increases. But could time ever reverse? Some models suggest that in certain extreme conditions, like at the Big Bang or Big Crunch, time might behave differently. Others wonder if in a quantum framework, information loss could be the true source of the arrow. And in certain interpretations of cosmology, the universe could run in both directions from a low entropy beginning, with time flowing outward from the center in both ways. In short, the laws allow it, but the universe doesn't seem to choose it. And yet the question remains, is the arrow of time a fundamental rule or just a cosmic habit? Are constants of nature truly constant? There are numbers that define the universe. The speed of light, the gravitational constant, Planck's constant, the fine structure constant, the strength of each force, the mass of particles. These are the fundamental constants, values we cannot derive, only measure, and they determine everything. But are they truly constant? Some theories propose they might have changed over cosmic time. Even tiny shifts would radically alter the universe. Atoms wouldn't form, stars wouldn't burn, life wouldn't arise. Astronomers have searched for clues in ancient starlight, distant quasars, the cosmic microwave background, hunting for signs of change. So far, no confirmed variation. But we don't know why these constants have the values they do. Why not different numbers? Why not a different universe? Are they fixed by deep logic or chosen randomly, perhaps from a multiverse of possibilities? In physics, constants are the givens, but someday they may turn out to be answers. The simulation hypothesis. What if the universe isn't real? The simulation hypothesis suggests that what we experience as reality may be a kind of program simulation, a virtual world running on some vast unknown substrate. The idea isn't just science fiction. Some philosophers and physicists take it seriously, pointing out that information, not matter, seems to be the true foundation of physics. Reality has limits like pixels, Planck length, quantum states, finite entropy. Our own computers are approaching the ability to simulate entire worlds, so perhaps others already have. Nick Bostrom famously argued that if any advanced civilization could simulate universes, and if they did so often, then we're more likely to be in one of their simulations than in the original reality. Of course, we don't know. We may never know. But the line between physics and computation is blurring. If we are simulated, does it change anything? We still feel, we still wonder, we still love. Perhaps meaning isn't in the substrate, but in the story we live. Is the universe finite or infinite? Does the universe go on forever? We can look far, billions of light years. But even that is limited by the speed of light and the age of the universe. Beyond that, we don't know. If space curves back on itself, like the surface of a sphere, it might be finite, with no edge but still enclosed. If it's flat and open, it could be infinite, stretching endlessly in all directions, filled with infinite stars, infinite matter, and perhaps infinite copies of you. Cosmic background measurements suggest the universe is very close to flat, so large that if it is curved, the curve is too subtle to detect. But flat doesn't guarantee infinite, and infinite doesn't mean everything happens, only that there may be more than we can see. Whether the universe ends or just keeps going remains one of the most profound open questions. We see a horizon, but we don't yet know what lies beyond it. The end of the universe. How does it all end? There are several possibilities, and each one is quiet, slow, and strangely beautiful. In the heat-death scenario, the universe expands forever. Stars burn out, matter decays, black holes evaporate. Eventually, only cold, dark emptiness remains, a vast, silent void, near absolute zero, where nothing more can happen. In the Big Crunch, gravity might one day reverse the expansion, pulling everything inward until the universe collapses in on itself, a fiery rebirth or a final end. In the Big Rip, dark energy grows stronger, tearing galaxies, stars, atoms, even space itself apart, until not even time survives. And in vacuum decay, our universe could suddenly tunnel to a lower energy state, rewriting the laws of physics in a cosmic instant. No matter the path, time stretches long beyond imagination, trillions of years, then more. The universe doesn't end in fire or ice, but in quiet. Consciousness and physics. What is consciousness? We think, we feel, we observe. But how? Neurons fire. Patterns emerge. But where is the line between matter and mind? Some theories treat consciousness as an emergent property, arising from complexity, like music from strings. Others suggest it may be fundamental, woven into the fabric of the universe. Quantum physics adds mystery. Does consciousness collapse the wave function? Is the observer part of the equation? Or is that just illusion? We don't know if physics can fully explain consciousness or if something deeper is needed. But we do know this. Without consciousness, there would be no story, no questions, no wonder, no awareness that the universe exists at all. Perhaps we are not separate from the cosmos, but the way it knows itself. Observation and reality. Does the act of observing change what is real? In quantum mechanics, the answer appears to be yes. Until measured, particles exist in a superposition, not here or there, but both. Only when observed do they choose a state. But what is an observation? Is it consciousness, a detector, an interaction? Some interpretations, like the Copenhagen view, accept collapse as fundamental. Others, like many worlds, suggest that every possibility happens. An observation just places you in one branch. At its heart lies a strange truth. Reality may be undefined until it is known. The boundary between subject and object is thin. When you look at the universe looks back. The limits of human understanding. We've come far, from falling apples to quantum fields, from orbits to uncertainty, from stardust to thought. But are there limits to what we can know? Some truths may lie beyond our senses, our language, even our logic. The universe may be governed by mathematics too vast, or dimensions too small, or structures too complex to ever fully grasp. Gödel's incompleteness theorems showed that even in math, some truths can't be proven. Quantum uncertainty sets limits on what can be measured. Cosmic horizons hide parts of the universe forever, and the mind itself is a product of the system it seeks to understand. Yet within those limits, we wonder, and maybe that is enough, to seek, to ask, to dream, to know just a little, and to be awed by what remains unknown. Ending. And now we've reached level 100. From the simplest ideas to the deepest mysteries, thank you for walking this path through the universe, one quiet step at a time. If this journey brought you peace, leave a like, subscribe, and share it with someone who might need a little wonder tonight. What was your favorite level? What made you pause, or smile, or drift? Let me know in the comments. And until next time, sleep well, dream deep, and never stop being curious.